Okie dokie. So we've got this rod being acted on by a couple of forces. Overall, we've got a full turning moment down going in this direction. So that being put in tensile. This one here will be compressing it. So the overall turning moment acting on that particular element is going to be a negative moment, if you like, or well, it's going to be in compression. So let's call that a negative turning moment. So we've got 3000 times by this one here to here will be 0.35, and then the other one will be plus 3000 times by 0.2. So you can factor that, can't you? So overall you've got minus 3000 times by what? 0.15. So that'd be minus 450 Newton meters. The other effect will be a torque, which we're given. Of 350 Newton meters. Okay. That's trying to, if I'm looking from above, looking up it, that's going to give me a positive twisting. So that'll be, I'll take that to be positive. Next thing we want to know about the J and the I. So what's the J going to be? It's solid, so straightforward. Pi d to the power 4 divided by 32. So that equals what? Pi divided by 32 times by the diameter, 0.032 to the power 4. So that's 1.0294. I should have maybe pressed the Eng button. Times 10 to the minus 7. Meters to the power 4. Okay, I'll use the trick that I equals pi d to the power 4 divided by 64. Come on. So that will be half of my J divided by 2. So that's 5.147 2. Okie dokie. So let's find the compressive stress. So that will be the bending stress. So that's going to be, does it matter what plane I say it's in? Not really. I'll call it bending then. It'd be, well, actually, it'd be actually in the Y. I'll call it the Y plane. So that's M over I. Distance away from neutral axis, which is Y. So my M is minus 450. My I is 5.1472. And my Y will be half the diameter, which will be 0.016. So minus 139.88 megapascals. And now my torsion shear stress will be a positive. So we got a torque, the J and the R. The R, of course, is the same as Y. So we have got the torque 350 times by 0.016 divided by the J, which is 0.10294 to the minus 7. And that's 54.401 megapascals. What do you want? You want to know the principal stresses at H, the maximum shearing stress at this point as well. So all you're looking for is the same as before. All we really need is this one on the formula sheet. Okay, so I'll do the same approach as I did before. I'm going to use this first. To find the maximum shearing stress. So that's going to be square root, open a bracket, zero, take away, so that'd be plus 139.88. I'm going to work in megapascals. Divided by 2. Square it. Plus 54.401. Square that. Let's find what that value is. So that is 88.4 0.606 megapascals. Yeah, so that's fine, that's correct. And the next, what I'll do is I'll do this trick of finding the average stress. Not that I'm interested in it. So that will be 0, take away 139.88, divided by 2, and that equals minus 69.94 megapascals. So my minimum stress on the element I've been asked to find the angles. Oh, principal plane. Yeah, I have to do the principal plane as well. Okay, so the minimum is going to be given as, type that number in so I can reuse it, 69.94. Take away 88.606 equals minus 158.55 megapascals. Come on. And then I'm going to reuse this, change my minus to a plus, and then get a maximum positive stress of 18.666 megapascals. So it does want me to find the principal plane as well, principal planes. I suppose I also should tell you which way they're behaving. Oh, I've run out of space. So we want to use this. And we'll want to use a transformation to establish which is which. Although we can probably guess. So we've got a stress state that looks like this, 0. Minus 139. Eight. 54. So let's find our stress planes. So that will be inverse tan. It's a negative -2 times by, oh no, it's positive, sorry, 2 times by 54.401, that's the top, divided by 0, negative to negative makes that a plus. Be careful with your signs. 139.88. Close that bracket, and that then tells me 2π equals 37.877. So the first plane I'll take to be divide by 2, 18,938 degrees, then a plus 90 onto that to get my second plane. That's 108 plus 994 degrees. Okay, so that's the two planes, and we now got to work out for this stress element which is which. So we've got a stress element pointing off in this direction, and another one's pointing off in this direction. We want to rotate our angle, therefore, by the 18.38 degrees. So we want to take this state and rotate it anti-clockwise by this amount. So let's do that for this x here. So we imagine we're looking at that x there. So what will become my new x prime as it's pointing in that direction? That will be 0 plus, unfortunately that's minus 139.88 divided by 2. Okay, so that's that bit there. Okay, plus 0 again. Take away. Actually, I can't remember. Was that a negative or not? Start again. Okay, let's do it properly. So we've got 0. Take away 139.88. Divide by 2. Plus, open a bracket. 0. Take away, so it's plus 139.88 divided by 2. Now times it by cos 2 times by, we're going to rotate it backwards by 18.938 degrees, plus the 54.401, and times that by sine 2 times by 18 0.938 degrees. Close the bracket, equals. And so that tells me we've got 18.666 pointing off in this direction. So I don't have to do all that calculation again. I will look back at my two results. So that's that one there. So the other one will be minus 15855. We could have guessed this, couldn't we? 158.55, I think it was. Okay, and then we want to find the shear state at that point. So we will be using the last one, our formula sheet. So we want to use this. So minus, open my bracket, so I've got 0, take away, so that's plus 139.88, divide by 2, times it by the sine, 2 times by, we're rotating everything back by 18.938 degrees, close the bracket, plus 54.401 times by cos, 2 times by, again, rotating that by 18.938 degrees, close the bracket. So that then effectively is giving me pretty much zero stress. I'll take that to be 0. Shear stress. Okay, so that can be modeled then as these two principal stresses, and with a shear zero stress in that direction. Let's check that with Arnold's answers. Do, 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 do. I don't think he went this far. Doesn't look like it. Okay. Where are you getting that number from? Have I gone wrong? Okay, don't think I have, but I will stop the video and just double check this in the book. If it's fine, you will not see me again. Okay, so I am correct. It's just I'm misreading the question a bit, so I just want to highlight the last bit of the question, which was the maximum shearing stress at the same point. and we've already found that result. So that's the 88.6 megapascals. But the representing this shear state, we can represent it like this shear state, but this on that shear state, if you like, come on. I think my computer needs to be rebooted. This doesn't equal the maximum shear. Okay, which equals the 88.606 from the previous result. Now what you could do is you could take these values and you could plug them back into well, actually we haven't done it, but you could take these two values and you could plug them into or rather those three values, I should say, and you plug them into here, and you'll get the 88.08 answer again, where what you're doing is you're plugging in like the shear prime, and this y prime there. So you can put these numbers here and here. This is virtually 0. Obviously just truncation, and then you'll again end up with, well, this result up here. Okay, so the 88.6. So yeah, everything's fine. Just need to remember that your maximum shear and stress is not your transposed shear and stress in this state.